Hello everyone, welcome to the lecture 8 of COMSOL Multiphysics training course. In this lecture, we are going to introduce the application builder in COMSOL Multiphysics. So let's begin. So as you may know, the COMSOL has two main features. One of them is the model builder. In fact, the model builder was the feature that we used to work on it in the previous tutorials, and we will be able to set up our model, build the geometry, and add the physics and compute for our case. However, it is only for one specific model. The next feature is the application builder, in which we can turn the model into a simulation app, and the simulation app can be a standalone environment in which we can solve our problem very quickly without repeating many steps. It is very useful when we have multiple variables, when we have optimization, and so on. So let's introduce it today. So to do this, we need to have an example as usual. In the example today, I'm going to solve a simple problem, which is how to find the relative permittivity of a foam. A foam is modeled as a solid structure with some porosity distributed through the structure. We simplified the porosities as circular shapes with the diameter of capital D, and the gap between the two pores is G, and also the permittivity of the solid structure is known as epsilon1. So these are the main variables of the system. In fact, we want to see by changing the size of the pores, the distance between the pores, and the properties of the solid content, or basically the relative permittivity of the solid content, how the overall permittivity of the foam is changing. Okay, so let's have some theory before going to the software. So for a rectangular shape structure, the capacitance is defined as shown in this formula, which epsilon r is the relative permittivity of the dielectric material. So the epsilon r can be calculated as the capacitance times the thickness divided by the permittivity of the vacuum and the area. And the permittivity of vacuum can be found on internet as this small number. So if we can calculate the capacitance of the structure, we can use this formula to find the relative permittivity of the structure. That's what we are going to do here. So let's develop an application for this system to find the relative permittivity of the system under different porosity and material conditions. Let's begin. Before we go to the application builder, we have to set up our model in the model builder. In this problem, for simplicity, we are going to the 2D, and then because we deal with capacitance, we go to electrostatics and add it as our physics. Then we use the stationary to do our case. There you go, we are in the model builder environment. Okay, one thing that I should mention before we go forward is we just want to have a simple case because our focus would be on the application builder. Okay, at the beginning point, we need to define some parameters. These are the parameters that we need them in the future. So I'm gonna start with D as the average diameter of one pore structure inside the foam. Like I said, we simplified the foam with circular porosities, and I'm gonna use 0.3 millimeter as the diameter of one porosity inside the structure. The next parameter is the width of our foam, which is 10 millimeters, and the thickness of the foam D is 3 millimeters. These are just some arbitrary numbers that I selected for our geometry. You can use your own based on your physics and your problem. The next variable is G, the gap or the average gap between the porosities, and I'm gonna use 0.2 millimeter for that. The next one is the number of pores in the X direction of the structure. Again, we use an isotropic distribution for the porosity through the structure. So I'm gonna use floor, the width divided by the gap plus the diameter. In fact, the function floor makes the number as an integer and remove the decimal, right? You may know this function from other software like MATLAB. In the y direction, we're gonna use the same formula, except instead of the width, we are going to use the thickness, right? So let's do that. We have d divided by g plus d, right? And the other parameter we need to define is E1, which is the relative permittivity of our solid content. For example, if it's a polymer, we can use 2 and it doesn't have any unit because it's a relative parameter. And finally, we have the permittivity of vacuum, which is 8.854 E minus 12, and the unit is important, which is farad per meter, right? That's it. So we are all set with the parameters and we can go on to the modeling. Now we are in the geometry and we need the overall structure of the system. So I'm gonna use a rectangle with the width of W and D. That's it. Build selected. This is our overall structure, and then I'm gonna use one circle as one pore. So the radius is D divided by 2, and position for the first circle we just use G plus D divided by 2, and same thing for Y, and then build selected. So this is one porosity, right? And then we can use the array function to distribute the pores through the structure. We did that before. We just need to select the circle. In the X size we use NX, and in the Y size we use NY, and that's it. And now we have to define the displacement. In the X direction, the displacement would be G plus D, and in the Y direction we also have G plus D. Remember, G is the average distance between the two pores and D is the diameter of the pore. Then we click on build selected, and there you go. We have the pores distributed through the structure. Like I said, it is a hypothetical geometry. We are going to focus on the application builder today, and then click on build all, and we are all set with the geometry. For the materials, we have air inside the pores and we have a solid content around it, which is the matrix or the solid structure. So for that we can use add materials from library and then build in, then we add air, and after that we remove the solid content, and for the solid content we use a blank material and we select on this. We need to define the relative permittivity of that, which we defined it as epsilon 1 here. As you see, for the electrostatics we just need epsilon, the relative permittivity, right? That's it. So we are set with the material. For the electrostatics, the out of plane thickness, I'm gonna use the same value as the width of the structure, and then for the boundary conditions we right click, add ground in the bottom, which means that the voltage is 0, and for the top electrode or for the top layer we apply a terminal boundary condition and we apply a voltage for that because we need to find the overall capacitance, and the value of voltage is 1, which is fine. We are set with the physics of the problem, and then we have meshing. I'm gonna use the normal mesh and build all. Okay, the mesh is done. It looks interesting. The last step is to solve it. We go to study and then compute and wait for solving that, same as what we did before. So the problem is solved, we can get the results. Okay, I'm gonna add another result. I'm gonna click on 2D plot group, and then I change the name to electric field. And I want to show the contours of the electric field. So I select contour, and then under expression, electrostatics, electric, and electric field norm. Why norm? Because the electric field is a vector, and if we want to show the magnitudes or the values as contours, we need to use the normalized value, right? So we use that, and that's it. I just want to add this as a random result because I'm going to use it in the future for the application builder, right? So I click on plot, and if I zoom in, you can see that I have the contours of electric field through the structure, right? Interesting. Okay, now we want to find the overall relative permittivity of the system, which was our main problem, right? To do this, we need to find the global capacitance of the system and then use the formula we have, right? I'm gonna right click on derived values and then use global evaluation, and here I'm gonna use permittivity just as the name, ER, and here under expressions we expand it, electrostatics, and we use terminals. I hope you remember that from my previous videos, right? And then we add capacitance, and this gives us the capacitance of the system. But we need to find the relative permittivity, right? So we are going to use the formula we have. So D, the thickness, times the capacitance, divided by the permittivity of vacuum, E0, times the area. And because we have the same depth and the same width, the area is W squared, right? As you see, the unit is 1 because it's a relative parameter, right? And the description, we can, for example, use ER for that. So if we do so and then click on evaluate, and if we go up, this is the value we have for the epsilon r, or the overall relative permittivity of the foam structure. As you see, the number is 1.6 something, which is less than 2, which is expected, right? Because we have a solid structure with the relative permittivity of 2 and air with a relative permittivity of 1. So the combination has to be something between 1 and 2, right? So we found the solution for the system. However, this only gives us the result for one simple simulation. And if we need to find the effect of the diameter of the pores, the distance between them, the effect of the relative permittivity of the solid structure, we have to repeat the whole process every time we change that and then solve and calculate. So why not we develop an app to do that for us, and we don't have to repeat that every time, right? So we are going to use the application builder now. To do this, we just go to the application builder and click on it, and this is the environment that we develop our application. If we click on model builder, we go back to the original page. So we just go to new form, and this is where we make the details of our application. For the title and name, we can use anything we like. For example, I can say permittivity calculator, and I'm gonna use the same name here. Okay, and now these are the three options that we should be careful when we want to select from them, right? Under input outputs, we have to find what we need to add as the variable and what we need to find as the results. So in this case, we have the D as the diameter of the pores as one variable, so we add it. The other one is G, which is the gap between the two pores, or the average distance between the pores, and the permittivity of the solid content, E1. So we add it, and what is the result that we're looking for is the permittivity ER. We also add that, and that's it. So as you see, they appear here, but don't worry about these values and numbers. The next window or the next option is graphics, where we add the windows that we are looking to show the results of simulation or the change of geometry as we change a variable. So for example, we can add the geometry and the electric field. That's why I defined that, because I want to show it here. So I added two graphics in here, and finally buttons. Buttons are the options that we add to the application, and once we click on that, it does the calculation for us. For example, we can add plot geometry, which means that if we click on this button, we see how the variable or the variables will change our geometry. And then compute a study. This is important. It means when we click on that, we solve the problem, right? So if I scroll down, they are added as two buttons here, and we are good. These are all we need for this problem to be added into our app. In fact, we have the variables, the graphics that we need to show, and the buttons to model in the app, right? So we click on OK, and here we can play around the graphics or the window of our app. For example, we can just play with the location of the windows. I'm gonna make it larger. This is the results from the electric field, and this one is the geometry. So these are the variables, and we have these buttons. I'm gonna put them up. So this is how our app looks like. We have the variables, we can change them, and then we can use these two buttons to show the geometry and compute for our problem, right? And we don't have to repeat all the steps that we had before, right? Once we are set with everything, we click on test application and wait to launch the application. And there you go. This is how our application looks like. These are the variable windows. We can increase, we can decrease, and then this is the value we are looking for, epsilon r, the overall relative permittivity of the structure. Let's do one case, and then you will see what happens. As you see, this is our initial geometry and initial results. So imagine I want to make the pores larger. For example, the diameter from 0.3 millimeters becomes 0.4 millimeters, and the distance or the gap between them will go to a value like 0.3 millimeters, and the epsilon 1 or the relative permittivity of the solid content becomes larger, for example 3. Alright, so we change the variables in the app, then we click on plot geometry. That's it. You see, our pores size and the distance has changed. We could represent that here. Next step is to calculate ER. So we click on compute and wait to solve the problem. As you see, we did no meshing, we did no material definition, and we didn't go through many other steps that we had before. And we will be able to change multiple variables at the same time. So you can imagine how it simplifies our problem. And that's it. And the problem is solved. As you see, we have a new value for the relative permittivity of the system, and we have a new representation for our electric field, right? So let's try one more time. I make the diameter of the pore smaller, the gap even larger, and the permittivity just a random number like 4. So let's see how our geometry looks like first. So as you see, we have smaller pores with larger distance between each other, and now we have to solve it. So compute, and that's it, nothing else. And we wait to solve this case. There you go, the problem is just solved. We have new relative permittivity for the whole system, which is the number that is different from the previous case. And then we have other results for the electric field distribution. I hope you got the idea of using the application builder for your own problem. So you can have multiple variables, you can have multiple graphics, and then different results. This is just one simple case because I just wanted to show you how to use that. So as we are done with that, we can just close it, and then you need to save it, remember. And once you save it, it saves along with your model builder. So every time you can open it and access your app. If you go to this application builder menu, you can add more applications under forms. Just click on new form and add it. And as you save it, like I said, it will be added to your overall model. So next time you open the model, you can go to the application builder and access your app and then use it for your own system, right? Just go to test application and try different numbers. Okay, I hope you got the whole point of using the application builder and use that for your own problems. In fact, there are other options under application builder that you can use, such as layouts, compiler, data access, record method, and so on. But for today, we just had the introduction on that, right? I hope you enjoyed today's video, so stay tuned for the next videos.